Hello, my name is Alberto Faria, and in this video I'll present our paper entitled BDUS, Implementing Block Devices in User Space. The storage services provided by modern general-purpose operating systems are typically implemented in the kernel. Compared to user space services, this boosts performance by avoiding the overhead of additional context switching and memory copies. However, kernel-level development is notoriously complex and is confined to an environment with limited functionality. This stifles research and innovation for today's increasingly complicated storage systems. In contrast, building these services at the user level has several advantages, such as easier development and maintenance, greater portability, access to more and higher-level languages and libraries, and improved reliability, fault tolerance, and security. This has motivated in particular the use of frameworks that enable the implementation of file systems in user space. The prime example of this is the Fuse framework, which is widely employed in both academia and industry. In our paper, we considered user-level development of storage services that work at the block layer. In Unix systems, this layer provides access to block-based storage via the block device abstraction, which is commonly used to expose local and remote hardware storage devices, as well as distributed storage systems. Briefly, a block device can be seen as a contiguous sequence of blocks, all having the same fixed number of bytes. Clients interact with the block device by submitting requests to it, such as to read or write data with block granularity. Block devices can be consumed directly by applications or through the use of local file systems such as ext4, which use block devices as their underlying data store. Many applications thus ultimately rely on block devices for storing data, and consequently, storage solutions that provide a block device interface are transparently and widely applicable. The behavior of a block device is determined by its driver, which is responsible for handling and replying to every request submitted to the device. For a storage system to provide a block device interface, it must thus implement a block device driver. These drivers are typically included in the operating system's kernel or provided as loadable kernel modules. However, it is currently possible to delegate their development to user space by leveraging existing subsystems not originally designed for that purpose. One such subsystem is Linux's Network Block Device, or NBD. NBD provides access to remote storage devices through a local block device interface. This works by running a user-level server in the remote host containing the storage device and configuring a local in-kernel NBD client to provide a block device backed by that server. Every request submitted to the block device is then transmitted through the network to the remote server, which serves it from one of its devices and transmits the reply back to the host that submitted the request. NBD includes a standard server implementation, but several frameworks exist that enable the construction of custom servers with custom request processing logic. These include BDUS, NBD-CPP, and NBD-Kit. Now note that if we use one of these frameworks to develop an NBD server that handles requests according to some desired logic, and if we then deploy this server in the same host as the client, joining the two through a loopback connection, we effectively manage to create a custom block device driver in user space. In other words, we create a block device whose behavior is entirely determined by a regular user-level process, which acts as its driver. However, the performance overhead imposed by this technique has never been thoroughly evaluated. We thus began by evaluating this approach. To do so, we developed custom pass-through drivers that simply redirect requests to an underlying hardware device, using each of the BDUS, NBD-CPP, and NBD-Kit frameworks. Then, we evaluated the throughput, latency, and CPU utilization attained when both performing several workloads directly on the underlying device and performing those same workloads on each of the pass-through devices. This allowed us to isolate and measure the overhead imposed by each of the mentioned frameworks. We used a total of 41 workloads, some performing operations directly on the block device under evaluation, and others performing operations on an ext4 file system backed by that device. Workloads operating on a file system were divided into three types: data-intensive micro-workloads, which performed only read or write operations on files; metadata-intensive micro-workloads, which created, read, or deleted many small files; and macro-workloads, which emulated the behavior of real-world applications. In the remainder of this presentation, we show only results for throughput obtained under a subset of the workloads operating on the ext4 file system, and using an enterprise NVMe SSD as the underlying device. More details and the full results can be found in the paper. This plot depicts the throughput attained by BDUS and NBDKit relative to the throughput of operating directly on the underlying device under several workloads. The NBDCDP framework is omitted as it never outperforms BDUS. Under the depicted workloads, we see that BDUS can reduce throughput by up to 93% and NBDKit by up to 48%. BDUS generally performs worse than NBDKit under multi-threaded workloads. This is because NBDKit can process several requests in parallel, while BDUS is limited to handling them sequentially. One major factor limiting the performance of all NBD-based solutions is that they use sockets for communication between the client of the block device and the user-level server that handles requests. This imposes an additional memory copy of the data being read or written, first from the client to a socket buffer, and then from there to the server, and vice versa. A second technique enabling the implementation of block device drivers in user space makes use of Linux's in-kernel SCSI target. Briefly, SCSI is a set of standards for data transfer between computers and storage devices. In this context, a target is a service capable of handling SCSI commands, and an initiator is a client that submits such commands to a target. Linux's SCSI subsystem includes a target core module in user space component, or TCMU, which enables SCSI targets to be implemented as user-level processes. Thus, a technique for effectively developing block device drivers in user space is to first implement a SCSI target with the desired request processing logic, then to deploy that target in the same host as a client, and finally to use Linux's SCSI initiator to create a block device that is backed by that deployed target. Unlike NBD-based solutions, this approach does not rely on sockets, instead using the UIO framework for communication between the in-kernel initiator and the user-level target. We evaluated the performance of this TCMU-based technique using the same methodology as before, and depict the results here by extending the plot shown previously. Despite this approach not relying on sockets, it still imposes overheads on throughput of up to 57% under the depicted workloads. Further, although TCMU outperforms both BDUS and NBDKit under certain workloads, it is surpassed by NBDKit under several others. Based on the results of our evaluation, we conclude that a categorical solution or framework for the development of block device drivers in user space should not hinge on existing subsystems designed for other purposes. We argue that better performance can be obtained through a clean slate design and implementation of such a framework, and that further improvements, both performance and functionality-wise, are also unlocked by removing the dependency on existing subsystems. We thus propose BDUS, a framework built specifically to enable the development of block device drivers in user space. Its design aims to reduce memory copies and system calls, and will provide a fully functional implementation for Linux. BDUS enables straightforward deployment of devices and provides facilities for replacing the drivers of existing devices with no downtime. This can be useful to upgrade or reconfigure drivers in systems with strict availability needs. BDUS also enables the recovery of failed drivers, again without interruption of service to clients, which is useful for deployments with stringent reliability and fault tolerance requirements. Further, our evaluation shows that BDUS incurs less overhead on both throughput and latency than existing solutions, while exhibiting lower CPU utilization. BDUS consists of two main components, the KBDUS kernel module and the libbdus user space library. Internally, libbdus relies on KBDUS, and all communication between the two is accomplished through a character device. Users of the framework can create block device drivers as regular user-level C programs that link against libbdus. This amounts to implementing functions to handle each type of request supported by the driver, as well as specifying basic attributes of the device such as the size of its blocks and its total size. By compiling and executing the driver application, a device powered by it is then created. For each request submitted to the device, one of libbdus's worker threads invokes the appropriate handler. In more detail, a request submitted to a block device created using BDUS first goes through the PESH cache and through the two-level system of software staging queues and hardware dispatch queues that is provided by the Linux block layer for all block devices. KBDUS then receives the request, inserting it into a control inversion queue, where it awaits retrieval. Next, one of libbdus's worker threads in the appropriate driver process performs an IOCTL call on the aforementioned character device, retrieving the request. Finally, libbdus invokes the appropriate user-defined handler in the driver to process the request. Replies then follow the inverse path. All communication between libbdus and KBDUS is accomplished via IOCTL calls, and on average, only a single system call must be performed by the user-level driver per request. Further, request payloads are only copied once from the client to the driver, or vice versa, avoiding unnecessary memory copies. We now show the relative throughput attained by BDUS and the remaining systems under the same circumstances as before. For the workloads presented in the plot, BDUS degrades throughput by at most 33%. In general, BDUS either matches or outperforms other systems, in the best case improving performance over existing solutions by 43%. The only two exceptions are the file server and web server workloads, under which NBDKit outperforms BDUS. However, this is due to the fact that NBDKit was configured with a total of 256 worker threads, while BDUS employed only 16. The reason for this configuration is explained in the paper. As mentioned before, Fuse is a framework that enables user-level development of file systems. BDUS and Fuse share the objective of transitioning storage services to user space. However, the two operate on different layers of the storage stack and are thus both orthogonal and complementary to each other. Nevertheless, many storage functionalities can be implemented both at the block and file system layers, such as compression, deduplication, thin provisioning, encryption, erasure coding, and replication. One may thus have to decide between using BDUS or Fuse as a basis for the implementation of a storage system or component. To make such a decision, it is important to understand the performance characteristics of both solutions. We thus evaluated Fuse's overhead by performing workloads on a Fuse file system that simply redirects requests to an ext4 file system, which in turn is backed by the underlying hardware storage device. This plot depicts the relative throughput attained by Fuse under that configuration, together with the results for BDUS that were already presented. We observed that BDUS surpasses Fuse's performance significantly under many workloads, especially under metadata-intensive ones. This is because Fuse requires intervention of the user-level file system driver to satisfy many file metadata requests. In the BDUS deployment, these requests are instead submitted directly to the ext4 file system. Because the processing of metadata requests often does not translate into operations on the file system's underlying block device, many of them can thus be served without communication with the BDUS user space driver. In summary, we find that existing solutions for the development of block device drivers in user space, which hinge on subsystems designed for other purposes, exhibit limited performance. NBD-based solutions, in particular, rely on sockets for communication between kernel and user space, imposing additional memory copies. Further, the dependency of NBD and TCMU-based solutions on subsystems tailored for other purposes limits the introduction of optimizations and features specifically relevant to the development of block device drivers in user space. We thus propose BDUS, a standalone framework built to enable such development. We provide a fully featured implementation for Linux, and our evaluation shows that it outperforms existing solutions in throughput, latency, and CPU utilization. BDUS further provides features enabling the replacement of running drivers and the recovery of failed drivers, in all cases with no downtime. In addition, we show that file system stacks featuring BDUS can perform significantly better than stacks that employ the Fuse framework, considerably so under metadata-intensive workloads. We thus argue that BDUS should also be considered when developing storage solutions that may be constructed at both the block and file system layers. This concludes our presentation. BDUS is an open source project, and you can find it on GitHub at the link on the screen. We hope that BDUS will be useful to the community and accelerate the creation of novel storage systems. Thank you for watching.
Thank you, Alberto, for the impressive work and great talk. So for the general audience, if you have a question, please feel free to raise your hand in the Zoom or type your question in the Slack channel. So far we have 2 questions. The first one is from Barbara. So Barbara, go ahead, unmute yourself and ask a question.
Hi, Alberto. Hi, Youngli. Thanks for the talk. It's really interesting because I'm particularly interested in NBD. First is that since last, I think, many years, there was no substantial research on NBD part. So because I use NBD in my project, so I know these tools are really good, but still there was a lot of scope to improve. So really enjoyed your talk. My first question is regarding this dispatch queue. Because I use Linux on the, I'm more interested on the multi-queue part. So I understand that this dispatch queue part is the hardware queue part, right?
Okay, so BDUS at the moment only always uses one hardware dispatch queue, which can sometimes be a point of contention or a bottleneck. It shouldn't be too hard to extend that to enable the use of multiple queues. Yes, the interest here would be potentially higher performance under highly parallel workloads. I believe we mentioned that in the conclusion of the paper. So we would probably also have one control inversion queue, per each hardware dispatch queue. And also interesting would be to have dedicated threads in the user level driver serving each hardware queue separately. That would likely improve scalability, yes.
Cool. The software staging queue, if I have understood correctly, this is basically similar to this NUMA node, the one which multi-queue Linux kernel as well uses this multiple queues, software staging queues.
Yes, those are exactly the same software staging queues from the block MQ. They are managed by Linux and configurable by the user, but usually they are per core, I believe.
Okay, perfect. And one more is just not a question, it's just an opinion. And the context switching, this is, always our main concern, people who do research on Linux and user space part. We have this context switching part. So, I mean, if you can, I think it's also mentioned in the talk. I did not read it, but just want to have your opinion that how significant is still this context switching in the current state of the library?
Yeah, so the kernels, the context switching is a measured source of overhead for this type of user space solutions. BDUS in particular uses only one system call per each request reply pair, so it improves the existing solutions a bit in that part. Also, we would like to, in the future, experiment with I/O viewing, which would probably allow us to reduce even further the amount of context switching necessary, the amount of system calls, and also batch system calls together. And also the polling features would further help with that.
Cool, yeah, thanks. I think I asked a lot of questions, so thanks for the panel.
Thank you. We have a few more questions lining up. So the next one is from Mickey. Mickey, are you here? Can you try to unmute yourself?
Hi. It was just a quick question. I noticed in some of the figures that NBD Kit appeared to be doing better than just the native original version. I think it was the web server workload. It seemed to be having 10% speed up. I just wondered what happened there and can we make it happen more?
Yes, first of all, nice catch. I think we mentioned that in the paper. Yes, we mentioned that in the paper. Basically, it increases throughput, but also increases latency. So it essentially is performing batching more eagerly. So it's a trade-off there.
Thank you.
All right, we have two other questions. The next one is from Christian. Are there any plans for upstreaming BDUS into Linux mainline?
Okay, not at the moment, but who knows, possibly.
Okay, sounds good. Yeah, we have a last question from Joe.
Hi, I was just wondering if it's possible to boot from a disk that contains the root file system over BDUS.
Nice question. In principle, it should be. I'm not sufficiently familiar with the Linux boot process to know if a user level process could be already running to enable that kind of thing. I guess the answer depends on that.
Okay, yeah, that was my concern, that by the time you need the root file system, the user space might not be running yet.
Okay. So yeah, I guess probably not at the moment.
All right, we're tight on schedule. So thank you, Alberto, for the great work and great talk.